YouTube, welcome. People who might be streaming this at some later date, welcome also. At the college, we believe that the future of architecture is multidisciplinary, and we host a range of design degrees that include graphic design, industrial and transportation design, game design, interior design, and architecture. We track future trends, emerging technologies, and advancements in practice. As part of the series, we have 2 more events coming up that we want everyone to know about. The last lecture in this regular series will be on Thursday, April 18th. That's next week. Our speaker will be Woni Arndt, who's the department head of product design at the University of Oregon and a partner in the design office Studio Gorham. And it says here that you're supposed to sign up on our COAD lecture page in order to see this. On May 2nd, we'll have our annual show of student work and alumni work, Show LTU. It's an industry and awards night. And we'll also have a guest speaker. It says here, the renowned, I would also add notorious, architect Tom Main of Morphosis, who some of you may know has done a building on this campus, and that ought to be very good, interesting. Today I'm here to introduce my colleague and friend, Ralph Nelson. You know, it's a lot easier to introduce someone that you don't know, because you just know less about them, there's less to say. So I called Ralph last night and asked him what I should say, and we considered a few alternatives. One of which would have been to do what's done at a lot of lectures like this, which is say to go through and read the resume. Actually, a few years ago, I actually saw the chair of a university architecture department introduce a speaker by reading the entire resume. Apparently, no, I'm not kidding, I actually saw him do this. I was warned that this fellow would do this. He read a list of all the schools that the speaker had attended, that speaker's awards and recognitions and honors, the names of the books he'd written, the titles of the papers and chapters he'd written. I think he added the guy's, hat size and his favorite color, a few things like that. It went on for quite a while. It was amazing. Ralph and I decided that would not be appropriate for today. Fortunately for you. I also considered another alternative. As Ralph is really only one of 2 Minnesotans that I know of, I considered taking the lead of his fellow Minnesotan Garrison Keillor and making up a bunch of lies about his life. How he ran away with the circus and was a Pulitzer Prize winning underwater welder and things like that. Ralph suggested that lying takes too much time. Although, Ralph, I disagree. Current political discussion in this country seems to indicate that lying is, actually it's overvalued, and it's rather efficient. Once you start lying, the words just seem to flow. So that could have been an opportunity for us. I could have made up things about you. What we decided on instead was that I would just introduce him as a friend and colleague. Ralph has been a friend since he arrived here about 10 or 12 years ago. And so we've had a lot of time to talk. In the last few years, we had time to teach together, which has been really enjoyable. And in fact, to collaborate, which I appreciate a lot. And I think that's one of Ralph's finest traits, that he likes to collaborate with his friends and colleagues. And with students, but not for his own sake, but to make things better. He is witty, and he is insightful about architecture. And I take from all of this, including my work with him in teaching, that he considers architecture not to be an indulgence, although, of course, if you value wit and intuition, those things can easily be included. But that architecture is really something that we do for other people. I only know of one architect, you know whom, who was able to somehow design 7 or 8 homes for himself during his career. It's 7 or 8, depending on when you start counting. But that's not the career very many of us will have, fortunately or unfortunately. Most of what we do is for other people, right? And to do that, we incorporate our best ideas, our intuition, our knowledge, but particularly we incorporate technological ideas, but all that to make a better place for other people. And that is the kind of thing we've tried to do. We've taught together, and what I believe Ralph will be addressing in some way today. So please welcome Ralph Nelson.
Thank you, Martin, for that wonderful introduction. Thank you all for attending today. Appreciate it. I will be talking about energy in architecture. And this presentation today is based on work that I conducted over the fall of 2023 during my sabbatical. And first off, I'd like to thank Provost Heiss, Dean Dalvin, Chair Geyer for supporting my sabbatical. And also I'd like to thank Margaret Wong, simply because she's amazing and super supportive and a great critic. And so she was essential to my work. The sabbatical was great because it allowed me some precious time to define a new scholarship trajectory for myself that would engage design, technology, and practice. It was also time for me to think about both societal as well as architectural issues and pragmatics and poetics related to architecture. And it was time to think and read and research and reflect, and for me, most excitingly, to design. There was a couple of additional questions that I started the sabbatical with. Pretty simple, but which buildings consume a lot of energy? And how do you know if they do or not? Can existing buildings produce all their energy needs on site and don't use combustion? Can existing buildings express both energy consumption as well as generation architecturally? And if buildings expressed energy, would society be more conscious of energy? Would society be compelled to take action? I'm going to primarily talk about solar energy today, in part because it's fundamental to architecture. You know, daylight, there is no architecture without daylight as far as I'm concerned. Contemporary buildings can engage the heat of the sun for solar thermal. I'm not going to talk at all about that. Contemporary buildings can also use photovoltaics to generate power for a building. That's primarily what I'll focus on today. And the talk today is really kind of three segments. I'll talk about the past, a little bit about the present, and then a future projection. So we've been burning fire for a long time for our energy needs. And fire was an amazing technological discovery, but why we're still using fire for energy transformation today, it just seems kind of primitive. Part of my research was looking at documentation from the Energy Information Administration, federal administration, and I love how you can actually track energy consumption for the entire history of the US. So literally they track it from 1776 all the way to, they have monthly reports. And this chart makes us, I guess, understand how our insatiable desire to consume energy has just increased exponentially over time. Of course, that's not only paralleled the growth in the US population, but really our deep desire for more and more energy. Looking at the different types of energy sources, I essentially distilled that for you all, and part of that is to try to build a logic for how energy sources have changed pretty dramatically, pretty quickly over time. And it helps us think about the future if we understand what's happened in the past. So for the first 75 years of the US, basically we used wood for all of our energy needs, right? What's interesting to me about that, it was very localized or regional. Most interestingly, every building somehow expressed energy in the architecture. It was fundamental to the character of the architecture. not only, and of course it's primarily through fireplaces and chimneys, but not only for the buildings, but actually how spaces were defined. I think it's an amazing place. I think it's amazing just because the energy expression, the expression of the chimneys defines the street. It gives it its emotional character. But you also can breathe the energy. Now, the downside of burning wood for fuel is you start out with a lot of trees, you start cutting them down, and pretty soon you're left with not much. So we actually were running out of fuel pretty early in US history. Another thing that I think is interesting about wood for fuel is you can actually see where the source of energy comes from. You can see how it gets transformed, and you can see how much is left. And that's right in your face. It's in your environment. So I guess luckily or unluckily, coal quickly replaced wood as a fuel. And coal had a good run of about, well, more than 75 years, but basically by the early 1900s, we were relying on coal almost exclusively for all our energy needs. And there was some amazing architecture that emerged, kind of classic Albert Kahn building, where the energy expression, again, these tall chimneys, were fundamental to the character of the architecture. But we also have long forgotten that this was what the environment was like when we burned coal. I still remember as a kid going to Pennsylvania and passing all the coal, basically the coal mines, getting on that hill just before you come into Pittsburgh, and right as you get to the crest of the hill, it was just black smoke and fire. The entire valley was filled with black smoke and fire. That was a reality when I was a kid. That wasn't that long ago. I think we also are all conscious about our extraction practices and how that relates to the environment. I think a lot of people want to do something about it. In the early 1900s, when our demand for energy started to increase, we actually were smart enough to turn to hydroelectric power. And that's still a major energy source today, but small in comparison to burning fuel. The great thing about hydroelectric, it's a technology. You're just basically using the latent energy in water as it changes level to drive turbines to generate electricity. So there's no fuel involved. It's just a harnessing of simple technology. And our mass electrification that happened in the United States from, just before 1900 until about 1950, when pretty much 100% of buildings were electrified, was in part based on leveraging hydroelectric power. The reason hydroelectric power seems kind of like a continuous ban for that period is because of the rise of other things. There was actually a whole ton, everyone knows the Tennessee Valley Authority, a whole ton of hydroelectric public works projects in the US, and most of those are still in operation today. So in northern Michigan, Sault Ste. Marie, 1900, they were wise enough to build a hydroelectric plant, taking advantage of the 25-foot drop between Superior and the St. Mary's River. That's still in operation today, provides a third of the energy for the UP, and it's all done without burning fuel. And also, this is an expression of energy in architecture. If your building actually has, if your building is a dam and water flows through it, that's expressing the energy. Unfortunately, not every building can have a dam or have turbines in it. So it's just the source can express energy, but not the delivery or the buildings on the delivery process. So in a transition from coal, we went to gas and oil. A lot of that discovery and technological innovation happened in and around this area, Ohio especially. How is gas and oil, which is essentially the predominant, natural gas is the predominant energy fuel that we use for buildings today, how does that get expressed in the architecture? Ultimately, it's just kind of like magic. We don't really know about it. Architects have kind of relegated dealing with energy aspects to engineers, And the best we do as architects is maybe hide it on the roof or put some screens around it, or sometimes the screens are more interesting than others, but essentially we don't care. And so this really made me think a lot about like how we perceive energy in society. And if something is not visible, you tend not to think about it. And if architecture basically hides the sources of energy, that's preventing society from actually being aware of the role energy plays in our lives. So what if it's visible to experience? What does that look like? In a way, old buildings used to do that, right? Another major energy source, fuel source, is nuclear, obviously. There's some issues about why we started doing nuclear. Part of it was leveraging technology from World War II, right? Dealing with atomic energy. Part of it was the amazing 15-year, 250% increase in electrical demand in this country. Again, it's like the beginning of our insatiable desire for electricity. This is a building and power plant that just went online in Georgia. Took 20 years to complete, cost $34 billion, and that turns out to be $15 and change per watt, and it's only 2.23 gigawatts, which, what does that mean, a gigawatt? It's a lot, but it's not a lot. It only provides electricity to a certain portion of the state of Georgia. That's it. Architecturally, it's an amazing expression, but I guess I kind of view this as, I don't know, chilling in a way. And you got to wonder how vulnerable this kind of system is. And we're still using fuel, and then when the nuclear fuel is spent, where does that radioactive waste go? This is potentially the last nuclear facility that will be built in America. There are no others that are supposed to be coming online. Japan got rid of all their nuclear facilities after Fukushima. But it is, I guess people call it a clean source of energy. Problem is also that these have to be built in somewhat isolated areas, and you're not going to have every building with its own little nuclear energy plant, right? If we look at how long comparatively on this energy timeline in the US it took for that one plant serving a small amount of people to be built, it was an extraordinarily long period of time relative to the changes that happened. So this kind of gets us to the present, where there's major energy transformations in the US. This is a DTE coal burning facility that's scheduled in 2032 to switch to natural gas. In part, the US government is forcing them to switch because their coal, basically the coal tailings, they put in unlined ponds. So that's not so good. But electricity, we all know that mass electrification is going on, right, in society. And electricity is going to be our primary energy source. Electricity is great. The majority of it is produced by coal plants and natural gas. The major problem with depending on fuel to burn is that 57% of the energy, source energy, is just lost in the process through extraction, through actually heat burning, transmission loss, all of this. So really, out of all that source energy we're using, primarily for fuel, only 43% gets delivered to buildings. So again, getting back to fire being primitive, like where else in society do we expect 57% loss as being acceptable? It just seems kind of bizarre to me. So starting to look ahead, some future projections. If we want to get by 2050 up to at least 70% renewable and start to wean off of fossil fuel and primitive burning, some things have to change. So this is just one view of how long it took to transition from wood to coal, and that was I guess, 50 years in this chart. Took 35 years to transition from coal to oil. And we need to go in, well, from this chart, 30 years, we need to get up to a major transition for renewables. So this is another way of looking at it. How long does it take to get to 70% of a particular fuel? So coal took about 55 years, same with gas and oil, that transition. So we've got 25 years to transfer to renewables. But 25 years seems totally reasonable when looking at it in this scaled time frame. And also everything happens faster today than it used to in the 1800s and 1900s. So it seems totally reasonable to me that we could do this. This can happen. And the sort of technologies that are emerging now, primarily wind and solar, those are also technologies that leverage existing energy sources. You don't burn fuel, you get into energy. And in 20 years, just with wind and solar, we've added 330 gigawatts. Now remember that 20-year nuclear project was 2.2 gigawatts. So we know that in 20 years, you can have 150 times more energy potential using wind and solar. So all the major US power industries are going to solar and wind as fast as possible. So all of the major growth is primarily in solar because it's the easiest and least expensive. Wind is great, but you've got some limits to it, but it's $1.55 a watt currently to do wind power. That's compared to $15 a watt for that nuclear facility, right? And then sort of industrial scale PV is right now about $1.06 per watt. Of course, you need a lot of area to do that. We were just down in Ohio on Monday to watch the eclipse, and we passed a bunch of wind farms as well as solar farms. So currently, Ohio has almost 80,000 acres of solar fields. In fact, there's one going up right at the Michigan border. This one is, I believe, in southern Ohio. The downside of this, of course, it's, farm field you're taking over, but also this entire 274 megawatt, it's huge, not 2 megawatt, 274 megawatt, a lot bigger than that nuclear facility. Most of the energy is going to the Amazon building that serves our needs. It's also distributed to the community to a certain degree. Now, utility solar, they're all in because they're energy companies, and it's only $1 a watt, so they're going to put up as much of this as they possibly can. At least it's not burning fuel. It's pretty good. I wish we had in this country a policy like France has, where agriculture and PV work together, and they don't have as much land as we have in the US. And actually, it's scientifically proven that plants do better under PV because you lose less moisture from the soil. So, why can't we do this in the US? We certainly can. MSU in 2017 took another strategy. They formed a power purchase agreement to erect 45 acres of solar carports on the MSU campus. Of course, they have giant parking lots just like LTU does. But they realized early on that even though, so it's a purchase power agreement, they didn't pay for the carports, they didn't pay for the PV modules, they didn't really pay for anything. An outside energy company came in and said, we'll front you this, you're going to pay us a steady rate over time. And MSU decided to do it because it saves them $10 million over the life of the system. And this is happening for more and more large institutions now because it's just way cheaper to do it. I wish LTU would cover our parking lots in this manner. The benefit of doing this is not just to save money or create clean electricity, but actually to take stupid parking lots and make them at least more interesting experientially. And so these are now used for tailgating parties, MSU. People have some sense of experience when you arrive to campus that there's a transition from a carport to a building, and you get some protection from sun, from rain, from snow. Personally, this wasn't designed by an architect, but I think they did actually a really good job in doing this. But architects aren't really involved with this at all, as far as I'm aware. So again, we have contemporary new buildings where PV integration is, I think, a no-brainer. It's relatively easy to do. Faris was telling me that architects should think about that early on so that the engineering can support it. But people commissioning buildings, there's just no reason to not budget PV because it'll pay for itself in about 5 or 6 years on any building. Some architects with new buildings, a very, very small percentage of architects, are actually integrating large PV arrays into their new building design, and the works are notable. They're net positive in terms of energy. So I think, for me, the future generally for all of our energy needs is going to happen through technology, not burning fuel. And for architecture, I think solar technology is the most obvious. And part of that is just we've got an amazing amount of latent energy that comes to the Earth every day just from the sun. It's just so obvious. So some more EIA charts. So basically, renewables have now surpassed nuclear and coal in terms of how we generate electricity. So that happened, you can see in the chart, it happened pretty quickly, just over the last couple of years. And if you look at the trajectory of wind and solar, right now wind is more than solar, but solar trajectory, it's going to eclipse wind production in the next year or two. And then it's just on an exponential rise. So there's a very interesting website I found, or it's actually an organization called the Solutions Project. So basically, they've outlined a strategy to get to 100% renewable energy by the year 2050. Right, that's where we want to keep global warming under control. And what interested me about this is that 25% of it is going to come from integrated PV with buildings, with architecture. So that just seemed to open up like a larger opportunity for architects and architecture to handle this. But also it made me think, well, what about the few 100 million existing buildings we have? How do those actually engage PV? So one of the things about electrification and going to renewable resources, we actually will reduce our demand by 51%, in part because we're eliminating all of those losses by burning fuel. People don't think about it, they think it's business as usual. And the amount of land that we need is less than 1% of the land and building area, so it's not out of the question. And really, I think everyone is now asking the question, like, what's the future of energy? And who's going to be affected by the energy future? And of course, the simple answer is everybody, everything, everywhere going into the future. So we all have a vested interest, but it may or may not be conscious enough. So a simple diagram for what I attempted to do on the design aspect of my sabbatical was just have a desire to express energy fully in architecture, but not through new buildings, through existing buildings. So the way I framed the design aspect of the project was I selected some common buildings and common building uses that have relatively high energy consumption. I sized an on-site energy generation system, a PV array, that would be equal to the energy consumption of that building. So this equals that. I tried to express the energy system architecturally, so it would have some redeeming, I guess, experiential qualities, aesthetic qualities. And then I selected only existing buildings to test out the idea, just to see if that was a reasonable broad application. So I think the in some ways, the societal benefits and the audience for this project is really institutions, municipalities, corporations, the general public. How can we improve awareness of energy and positive perceptions of identity, mission, or brand for an institution or a municipality or a corporation? Like, public perception is everything. How can we also enhance everyday functions and maybe introduce additional functions by implementing large PV arrays that are integrated with the architecture? How can we also maybe think about creating more energy independence for buildings, because we're going to have to decentralize our energy system in America? All the predictions going forward is it's going to be smaller and smaller scale. We're too vulnerable. The system is just too overtaxed. You know, we get all of our power outages through DTE on a pretty frequent basis now. And ultimately, we can improve existing buildings by decarbonizing one building at a time and reducing operational costs for the building, right? So what are the benefits to architects for all of this? Certainly alternative practice opportunities for essentially adapting existing buildings and sites with large PV arrays. And if we assume that several million of these buildings are going to go through this change in the next few years, architects should be a part of it. They're almost out of the picture entirely right now. But architecturally, it gives you an opportunity to create new space and form. It allows you to design with light and shadow and with structure, things I love about architecture. And you can improve everyday functions with both poetic expression as well as an enhanced user experience. So those all seem like good things, good benefits. So the here's six building uses that I chose, in part related to their energy use intensity. So if anyone is wondering what energy use intensity is, basically it's just the amount of energy it takes to operate a building on an annual basis based on the square footage. And there's two types. There's source energy, which is not only what the building uses, but all of the energy required just to get energy to a building. Site EUI is what I used, which is just the energy the building uses on an annual basis. And government has a fantastic website where you can actually identify site EUI for different use types that are also related directly to the specific climate you're in, because obviously buildings in different climates have different energy uses. So all of the projects here used our climate 5A, which is a cold climate, in terms of defining the energy per square foot intensity use. In order to size PV arrays to meet that energy, or once I found out the energy use of the building, I used a PV watts calculator, which I've used a number of them. I found this one to be the most accurate in terms of validating it with real world buildings. And so basically, I just put in numbers, values that are related to the specific context I'm working in, and then adjust the size of the array to equal the amount of energy, annual energy produced each year that a particular building needs to have. So that tells me then, like, how many PV modules I need. So basically the 6 sites I all chose in greater metro Detroit, and I'll take you basically on a tour of those 6 buildings. The first one was Trader Joe's. So this is the brief version of some of the energy calculations I did. So it just so happens grocery stores, supermarkets have a very high energy use, in part because of their operating hours. They also have freezers, coolers, these sorts of things. Trader Joe's, they're relatively small buildings, but because of the energy intensity, they actually consume a lot of energy every year. And basically what I did in some of the calculations, I determined the building size, the size of the site, and then I figured out how many PV modules I needed in order to meet the annual energy needs for each of the building, right? So that's where all these numbers come from. So this gets translated into the design. I did also an economic kind of run through of all 6 buildings. This is just shows you one of them. But basically, if Trader Joe's put a large PV array in their Michigan store, their their return on the investment would be a little over $9 million. So what corporation doesn't want to have a higher return on investment, right? So this is a beautiful Trader Joe's right now. They have the dumbest buildings. They put no money into architecture. The parking lots are always crowded, and they're kind of ugly, right? So, okay, this is what it looks like now if you're coming south on Woodward. So that's if you add a canopy. So first, it gives them presence on the street. Second, when you go into the canopy, there's actually a space there. It's not a nothing, still crowded as ever. But the space can be animated, modulated with light and shadow. And we can put the columns down that cars won't run into them. And some other features, you can add a skylight system, take away the PV, so you actually have a covered entry. So these are super pragmatic things, but actually begin to enhance the everyday experience of a really stupid building and a bad parking lot. And essentially, it's kind of inspired by, this is the old Le Hall Market in Paris, this idea that cars and market and overhead canopies can all coexist and also kind of work to improve the overall environment or architectural environment. So basically, in terms of kind of going through how I worked through the design, did several iterations. Solar south is, you know, up and down, heading down, and then Woodward is off to the side. Here's the large PV array that fits in. So the way this would happen is basically you have to define the structure of the PV array in relation to the structure of the building. The structure in the parking lot is related to the spacing of the parking lot. You add horizontal structure to support. You'd add your skylights for the entry. You would add the rails to hold up the PV, and then the PV all goes in biasing towards the south I went through a number of scenarios for tilt angle, overall area, overall production. But basically, this is what it would be in context. And at a detail, basically each individual module is oriented in such a way to kind of optimize its effect. But what's most interesting to me is to think about a PV module more like the petals of a flower or the leaves of the tree. Now, we all find trees and flowers, I think, beautiful, and that petal quality is a certain aesthetic quality. If we thought about PV modules not as just dumb things for an engineer or practical things, but how can we express them architecturally, I think it'd be more interesting. The second project is a BP station. This is basically at Woodward and 94. Beautiful building. This is, I don't know why they have such ugly buildings for a major oil corporation. You'd think public perception would be important for them. Their annual profits of, you know, $13.8 billion in 2023 suggests that they have some money to spare. They spend about $200 million a year on advertising. You think, well, isn't public perception really important for energy countries or companies? And what can they do to actually increase general public support for their endeavors? Basic calculations. So in this case, a gas station convenience store is a super high energy use intensity, but they're typically small buildings on relatively small sites. So you have to have a lot of PV modules in order to equal the energy that the building uses, but you've got a small limited area. So this is what the station currently looks like, and this is what the future station looks like. So this idea of creating a canopy that first and foremost establishes a new identity, a public presence for BP, and maybe is just a more interesting experience for the gas station. It was inspired by Ed Ruscha's sort of study of gas stations, filling stations as icons in the American landscape, but also a major mobile rebranding that occurred in the 60s where an architect, Elliot Noyce, teamed up with Chemaev for graphic design, and basically a whole fleet of mobile stores were built across the nation. A lot of those still exist today. It was important for mobile to change its image. I think it should be important for BP to change its image as well. So part of what I like about this is that, you know, most of the energy used is just for pumps and then the refrigerators and coolers for the convenience store part of this. So the idea is that you literally see the energy of the PV transforming down into areas where you have the coolers on the inside. And when you look up, you can actually see that architectural effect. So in terms of how this works, again, particular orientation on the site. First, get rid of the old canopy, add new support within the building. The structure for the new canopy could be some sort of carbon fiber or a mix of ETFE and carbon fiber. Rails for the PV, and then finally the pedals. And so its presence on the site, or the Google Earth view, also has something to do with projecting what BP is about. So this is a service station built in Dubai for a major exposition. And this could have had PV, but they actually have an off-site PV that powers this building. And then these are basically just skylights over the canopies. It does have a carbon fiber structure, and basically it's got a light and magic show underneath that goes on. So interesting, but doesn't really address energy. It does address architecture. I think it's pretty awesome, but I wish it actually addressed energy. Next project was Cass Tech High School near downtown. Some of you may know it. This is what the building looks like now. It was actually a brand new building in 2005. Cost $127 million at the time. They didn't budget anything in for PV array, although at the time that would have been the perfect time to do it because it would have paid them back tenfold by 2024. They have major energy expenses, giant building, 240,000 square feet. I don't know how many square feet we have in the LTU campus, but you know, they have 2,400 students, 140 some staff. So it's like a little village. It's a huge complex. And the architecture, you know, I guess it's interesting, sort of got a tech kind of quality to it. Surprisingly, schools, universities even more than high schools, are pretty intensive energy users. And in order to have a PV array that equals the amount of energy used annually for this high school, you need 7,667 modules. So a really big system, almost 4 megawatt system. And you need about 360,000 square feet of space to support that. This is what the building looks like if you approach from the south right now. And this would be the impression when you fit it out with PV. So part of it is just defining the main entry off of the giant parking lot. And so the entry gives you a connection, a transition between parking and the building, a little shelter. And as you move along the building, heading towards the back, you kind of look to the right. You see the whole service corridor is actually also tricked out with support for PV. But the more interesting thing is the football field, and it's now a football stadium. And the football stadium is just the PV supports and the PV array. And the PV system is integrated with the building in a somewhat strategic way, elevated off the roof deck so you can do maintenance, but also trying to support the existing architecture or complement the existing, I guess, tech nature of the architecture. And then the PV modules actually have a tilt on the diagonal, so they're all tilted directly south, even though the building and the urban grid are different. This is essentially the footprint, football field, building, giant parking lot. First adding structure and the PV modules in the building, extending out into the service area. So this is still only about half of the modules required. So then actually defining the south entry and west entry with PV in the field, and then finally the stadium and the parking area. And then, of course, it's essentially branded for the Google Earth view of Cass Tech, right? The C and the T. And then on Friday night, the football stadium illuminates, and you get some experience. Next building up, Ford Museum, Henry Ford Museum. 1.7 million visitors per year, so huge number of people that see this building. So it's on the National Historic Register, 1929 building. The front 800-foot-long facade is actually built with buildings that are just copies or replicas of buildings at Independence Park in Philadelphia. But then there's a gigantic, essentially, warehouse behind it, which is the museum itself. It was originally called the Edison Institute, and I like this 1920-some quote from Thomas Edison, kind of asking, why do we still burn fuel for energy? And he was totally invested in putting money in solar energy, and I like his prescient thoughts about not waiting until oil and coal run out before we actually leverage that technology. And again, this is 100 years ago that he's thinking about this. So the Ford Museum is a gigantic building, more than half a million square feet, really huge. Museums have pretty high intense energy use, and so this one needs an almost 7 megawatt system, which is pretty huge. Pushing 13,000 PV modules and 400,000 square feet of area that's required. So this is what the building approach would be like, preserving the historical portion of the building, or the pretty side of the building, having the PV kind of hover as a backdrop. So basically, this would still be your perception of the face of the building. But as you get to the west end of the building, where the IMAX theater entrance is, there's a solar carport, the beginning of a solar carport that is fairly large, but also respects the historic entrances along the west side and creates, again, a kind of sequence of entry, interesting architectural space and form. They have several courtyards. The courtyards are actually used for weddings and other parties rented out. There's these historic towers that sit inside. So the PV just kind of helps define those spaces, so that's what the courtyards look like. And then when you get up on the rooftop, you see that the entire building has this whole series of undulating roofs. And basically these were formerly light monitors that ran the entire length of the entire building. So the PV array is elevated above for practical reasons, but also you can open up these moments where, if in the future you want to admit daylight back into the spaces, you can. So this is what the structure of those roofs like. It's basically just like a factory construction, right? The whole building used to be naturally daylit, but by the 1970s, single pane glass and metal frames just wasn't doing it with the energy crisis we had in the 70s. So basically they sealed them all up. So that's what it looks like today. Which, the museum's still interesting, but architecturally it's not so nice on the inside. So if you wanted to reintroduce daylight, and part of they devote 15% of their square footage to power, innovations in power. And I'm thinking, well, where's the current innovation in power or energy in the current building right now? But if you wanted to introduce daylight, a curator would strategically define the zones where you could introduce daylight. The PV array would essentially support that, or you'd modify the PV array to do that, so that all of those things get integrated and you can add or enhance future functions and experience. So same thing here, you'd introduce daylight first. The whole building needs to be re-roofed, and actually the mechanical systems need to be replaced. It's like a $10 million project just to do that. But it would be actually less money just to put the large PV array on. Building and then site work. So that's what it looks like in context. And of course, this is Ford, so we know what Ford has been saying and their commitment, I guess, to going all electric with their vehicle fleet in the future. What does it say about the brand, the identity, the public perception? I think this makes sense. Next on line, a mosque, Mosque al-Salam, which is south of Dearborn, or in Dearborn, but north of the giant Ford facility where they're basically dumping coal every day. The community center, the mosque, they took an old warehouse industrial building and basically just renovated it for use as a community center and a mosque. Religious buildings have a relatively high energy use also, and in this case, it required a large number of PV modules that could be accommodated on the overall site and building, but just barely. So one thing that was interesting about doing the mosque is, when you do PV, you have to think about orientation, but the most important orientation in the mosque is to Kaaba, right? The Qibla, or the orientation. So this happens to be the orientation to the Kaaba, and I don't know if any of you know how that is calculated. There was actually a lot of controversy on how you determine that direction correctly. But from Dearborn, it's actually, you have to go north, because going north is the shortest distance around the Earth, the sphere of the Earth, to reach Mecca. So that orientation happens to be north, even though we know Mecca is south of us. Interesting that whole Qibla orientation basically used to all be done just with sun and shadow to determine what the proper orientation was. So in this case, solar orientation also works with the Qibla orientation, and then the other orientation that the building has is to the industrial train line that was put in. So the convergence of these three different orientations was interesting to me. This would be approaching the building from the east, and this would be with the addition of the PV canopy. As you come around, you see the mihrab, basically the niche that orients towards the Qibla. And the arches essentially are like a simple steel or aluminum frame support, but the idea is that it would be like a light and delicate version of what is kind of traditional element within Islamic architecture. Old mosques, but also contemporary mosques, typically have an exterior space that allows you to transition from the outer world into the prayer hall itself, and that's just a play of light and shadow. So this is what the parking lot would be like. And as you approach the main entry, see the approach. The PV modules cast their shade and shadow to the parking lot, kind of invoking the sense of the prayer rugs oriented to the Qibla within the space. So it's like a spiritual prelude to going inside the building. Actually, the building's not so interesting, so I think this might be more interesting. You also get a new rooftop deck space, and if you go up on top of the deck, you can see that a number of new daylight monitors have been introduced, and the top of the monitor is oriented due south, skylights on top, but then they splay over to meet the building structure in the urban grid, so that's what it looks like from above. And from below, within the space, you see how the kind of structure and transformation occurs geometrically, and then the solar cells actually perform kind of similar role to the traditional light screens or scrims in both traditional and contemporary mosque design. And so this would be what the space would feel like in the future. This is the existing mosque space, and acoustic tile ceiling and fluorescent lighting doesn't really evoke spirituality to me, but I think transforming it with daylight and also being able to physically see the prayer rug orientation to Qibla, because the prayer rugs are set directly to face Mecca, and then the building orientation in gray, and then the solar orientation in yellow. All those things are physically perceived at the same time. Basically, the process would be opening up for the daylight, adding vertical structure, horizontal structure, the PV array, and then the final modules. So I didn't realize, but there's a whole movement internationally to actually have mosques go to PV arrays for all their electricity needs. Especially in Jordan, the government basically supports PV modules being installed on mosques just to reduce energy costs, make them independent. So the final project is the Skillman Library. I don't know if anyone's familiar with this. It's been closed for a couple of years. The Detroit Public Library System has some issues, lack of financing, lack of generating revenue, a bunch of deferred maintenance on a lot of buildings. I don't know when the Skillman will reopen, but it's been closed since they've been developing the Hudson site. Libraries have fairly high energy use, in part because you have temperature and humidity control. So in this case, it's a big building that has more square footage in the building than the actual site, but you need, and so the site's 33,000 square feet, but you need 90,000 square feet of PV array. So what are you going to do about that? So if you approach the library on the People Mover, which I don't know who takes the People Mover anymore, but the idea is that this would be a part of the new architectural experience where a digital billboard generating income for the library system would be mounted. As you get off the People Mover, you see this kind of work of urban infrastructure, and as you kind of move around the base and head towards the entry of the library, you'd look up, and this is what you'd see when you look up. And if you're in the parking garage across the street, this is what you'd see looking down. If you were in Campus Marches looking towards the new tower, on the tall, super tall tower on the left, the new PV system would be to the right. The Skillman Library is to the right. And if you're coming from the baseball or football stadium, you'd see this slim tower rising up, trying to compete with the new Hudson Tower. And so this obviously was inspired by the current rage of doing slim towers for tall buildings, but also the kind of wonderful urban infrastructure that's part of a lot of cities. The fact that you can use billboard structures, we have no problem, using pretty intense structures for billboards, and the sense that you create an urban place with light and magic. This is a view looking down on the library with the PV array to the north. This is the south view. In terms of construction, the monumental arch goes up first with the support structure, then essentially the blade or the tower, and then all of the PV modules required. Again, the energy, visible energy expressed is the energy used by the building. So in this case, you've got a limited range of how sunlight can actually strike the PV array. So that was part of the calculations, and that's why you actually need so many more PV modules for this. But there's no reason why you can't insert something like this in an urban area. This would be the falcon view or the red-tailed hawk view of the project. It's really tall, but it's way shorter than the super tall building next door. And at night, the library could project messages out to the city of Detroit. So I'm really curious to have some feedback whether you found this interesting or meaningful at all, or if you have any other ideas for how I further develop this. So thank you.
Thank you, Ralph.
I'm right on time, sort of.
All 300 slides.
Yes.
Do we have questions or comments?
I have a question. Thanks, Ralph. That was great. Good to see you again. I have two questions, or one thought. There are some smaller energy producing systems, such as in Detroit we had trash to energy. Mm-hmm. And then I worked on a project when I was a sales engineer that was methane, so excrement from cows.
Yep.
To harness energy. Are those just too small for your study? Or
well, I mean, the energy question, I'm like a half of a percent of the big energy picture. But the bottom line is, don't burn stuff.
Okay. Right,
so all these other, we're going to have to rely on a bunch of energy sources, but the less you burn, the better it is for everybody and everything.
So my other question, though, architecturally, is in these solar collectors, panels, PVs, the energy has to be stored somewhere.
Yeah, so that's
Can you
another
talk
aspect
about
of this.
how that integrates into the building system?
Yeah, so energy storage technology ramping up exponentially. It's mostly at a super small scale or a very, very large scale, but all these technologies, in fact, our LTU accelerator, right, they're promoting battery technology companies to actually develop. I mean, we need to get to solid state batteries, but energy storage can happen through batteries, but also through ice storage and other forms of transferring energy through heat. All of that is, it's way outside of this study, but it's essential to, I think, the longer term success of just using PV or solar generated energy. But there'll be other supplemental systems, and that's where, I guess, natural gas or burning fuel or nuclear is still a part of the energy equation to kind of cover those times where you're not actually generating energy. This. And just what can I actually handle and what's meaningful in that window of time. But they're good questions.
We have an online question from Leslie Lynch Wilson. How would you use PV modules in downtown areas where there is only public parking lots behind buildings?
Yeah, good question. Well, part of it would either go vertical, elevate. Downtown Detroit, 31% of the land area is devoted just to parking. That's the actual land area. And you got shade and shadow, but even when you have partial sunlight available, it still works. In dense urban areas, you're going to have much more limited PV. But dense urban areas are still a small percentage of the total buildings and land area and parking lots that we have in America that all could be transformed. And I think one of it's a great online question. I think part of it, and I don't know if I was clear enough about it, but making the energy is just one part of it. I think the public perception about what energy looks like is like the critical thing. Because we're not going to do anything about it if we just press a button and we get energy. Because it seems like it's a miracle and we don't care about where it comes from.
Very interesting. Thank you for sharing that. Do you have plans to share any of these plans with the sites that you selected for your study?
Yes. Yeah, I mean, part of, this whole, if this is a new avenue of scholarship for me, I've got to get funding for more research. I need to, disseminate the ideas. But this is just, I'm just trying to frame the whole trajectory with all of this. But again, I said the audience in some ways is not really architects, or maybe not even you guys here, although I appreciate you being here, but it's really much more for institutions or corporations or larger communities to understand what is possible. So, but thank you for asking that.
Yeah. A suggestion for the architect, when they do the design document for any building, just put an extra load, dead load of 10 pounds per square foot or 15 pounds per square foot on the roof. That will carry no additional cost to the building, so that if they want to put anything on the roof, they have it. As I talked to you before the lecture, we have a building, we study everything over there, but the cost was too much. The guy cannot carry it because you need to repair the floor joists, you need to repair the columns.
The easiest time to do it is before you've even started designing the building, and just get everyone on board.
Just add it from the beginning. Add it from the beginning. Everything will be good. And the problem is with the long span structure. Short span structure don't have that problem. The long span structure will create more problems. And then another question: Probably I missed it, actually, probably talked about it. What's the cost per square foot for adding the, or just adding an electrical, support for the building?
So there are many ways of calculating it, and the smaller the scale, the larger the scale, the easier it is to benchmark it. But for building support structure, like architecture, or a building, a parking lot, all of the support structure, the whole kit and caboodle, it's about $1. The current rate is about $1.76 per watt. So it's not cheap, but you got to project, so you design it to have a minimum of a 30-year lifespan, minimum. But PV modules don't just shut off, they don't just stop working, the power diminishes gradually over time. So so usually the payback period depends on size and scale. It could be anywhere from about 3 years to about 10 years. But then after 10 years, even worst case scenario, after 10 years, it's free electricity. Other than whatever maintenance you need to provide, but it's free electricity. And buildings are being electrified more and more now. We're going to get rid of natural gas in buildings just because electric heat, cooling, ventilation is less expensive than using natural gas.
Thank you.
Yeah.
Are there any more questions? Are there any online questions, Andrea?
No.
Ralph, thank you very much.
All right, thank you, appreciate it.